Today we are going to learn about active actuators. So far, we have looked at the dynamic of rotating systems to understand how torque affects a spacecraft angular momentum, including environmental source for disturbance torque. We then looked at the various types of sensors used to measure attitude. Finally, we discussed the different types of actuators, passive and active, used to generate torque that allow us to change a spacecraft attitude. Then here we take a look at the brain of operation, the controller. The controller's job is to generate command for the actuators to make the spacecraft point in the right direction based on the mission requirement for accuracy and slew rate. To use the information from sensors and continuously adjust actuator command, the controller must be smart. To do this right, the controller has to keep track of what is happening now, what may happen in future, and what happened in past. Active control system sense the spacecraft attitude and supply a torque command to alter as required by the system. This technique also requires energy-consuming attitude actuators and is supply a good attitude accuracy in all three axes. In overall, thruster is able to provide any level of demand torque, and this capability makes this device suitable for the attitude control, nutation control, speed rate control, momentum unloading, and orbit control purpose. However, satellite lifetime is highly dependent on the quantity of fuel carried on board the satellite. The thruster must be on-off operated, and proportional control usually is not feasible. It also requires redundancy to make the system more complex and expensive. However, it is fast and powerful, so it is being a standard equipment on main spacecraft such as Space Shuttle and re-entry capsule. A set of orthogonally aligned torque and rod wired up so they can generate a magnetic dipole field of either sign. They can generate a magnetic field of arbitrary orientation. This artificial field interacts with the Earth's magnetic field to produce a net external torque on the vehicle that will tend to line up the field. This torque only has 2 degrees of freedom. Instantaneously, the torque rod will tend to align the vehicle and Earth field, with no control of rotation of the vehicle around its magnetic pole. The momentum control device actively overrides the angular momentum of small rotating mass within a spacecraft to change its attitude. How can this work? If you sit on a chair with bearing holding a spinning bicycle wheel at arm length, you can cause yourself rotate by tilting the bicycle wheel to the left or right, as you see from the demo video we conducted last semester. This works because the total angular momentum of a system is always conserved. As the bicycle wheel rotates one way, you rotate another to compensate, keeping the total angular momentum constant. There are 3 approaches to momentum control device. First, bias momentum system. It's a momentum wheel that typically relies on a single wheel with large fixed momentum to provide overall stiffness. Second, zero bias system is a reaction wheel that relies on 3 or more wheels, normally with little or no initial momentum. Each wheel spins independently to rotate the spacecraft and absorb disturbance torque. Third, control moment gyroscope rely on 3 or more wheels, each with large fixed momentum. The wheel is mounted on gimbal. Rotating the wheel about their gimbal changes the satellite orientation. A control moment gyroscope is an attitude control device generally used in spacecraft attitude control system. The particular CMG consists of a spinning rotor and one motorized gimbal that tilt the rotor angular momentum. As the rotor tilts, the changing angular momentum causes a gyroscopic torque that rotates an aluminum frame. A control moment gyro CMG system is a torque for 3-axis attitude control of an artificial satellite. A CMG consists of a flywheel rotating at a constant speed, 1 or 2 supporting gimbal and motor which drive the gimbal. A rotating flywheel possesses angular momentum with a constant vector length, and a gimbal motion will change the direction of this vector and thus generate a gyro effect torque. There are two types of CMG unit, single gimbal CMG and double gimbal CMG. A single gimbal CMG generates a one-axis torque. A double gimbal CMG generates a two-axis torque. In both cases, the direction of the output torque changes in accordance with gimbal motion. For this reason, a system composed of several units is usually required to obtain the desired torque. This is an example how the CMG is mounted on the satellite.